This is OPTI 380A, Lab 8, Lasers. I'm Zeller.
I'm Sophia Centeno.
And I'm Ethan Luker, and our TA is Liaf.
In Part A, we used an aligned helium neon laser cavity to achieve lasing and observe its transverse modes. The setup included a helium neon gas tube, a semi-transparent mirror, wire crosshair, alignment laser, optical rail, and note card. We observed the amplified beam passing through the mirror, crosshair, and lens onto the screen. By adjusting the curved mirror's tip, tilt, and rail position, we produced several transverse modes TEM 00 through 03 and 11, seen as circular patterns on the note card. These modes showed how minor mirror adjustments shape the beam and affect overall laser performance.
This is Part B of the Fabry spectrometer. In this section, we use the Fabry spectrometer to analyze the longitudinal modes of Henny laser. The system consists of two partially reflecting mirrors that create multiple interference fringes as the cavity spacing changes, allowing us to resolve the frequency spacing between laser modes. We first set up the laser, lined up with two mirrors, and centered the beam through the input iris. Using the oscilloscope connected to the Fabry detector, we observed repeating multi-loop pattern with each representing one free spectral range equal to 1.5 GHz. Using the oscilloscope, we measured the time separation of these lobes and plugged them into the equation below to find the laser's longitudinal mode spacing. We compared the measured spacing to the theoretical values using the laser cavity length. We had some error, most likely due to having an older oscilloscope and non-precise cavity length measurement. Overall, this experiment demonstrated that the Fabry interferometer can be used to measure and separate the frequency modes of a laser.
In Part C, we compared the spectra of a helium neon and red diode laser using an optical spectrum analyzer. Each beam was aligned through mirrors into a fiber port connected to the OSA and analyzed using Thor Labs. The helium neon laser produced a single peak near 632 nanometers, with an intensity of about 150 nanowatts per nanometer and a narrow 0.044 nanometer width. The diode laser showed several peaks near 651 nanometers, a broader width of 0.75 nanometers, and a weaker intensity around 43.75 nanowatts per nanometer. These results showed the helium neon laser emitted a single wavelength, whereas the diode laser produced several wavelengths, indicating key differences in their outputs.
Part D, ESA. We used an ESA to observe frequencies between two modes of a Henny laser. When light from two different frequencies hits a photodetector, the electric fields create a beat signal whose frequency follows the equation shown. We focused the laser onto the center of the detector connected to the ESA. We adjusted the laser until two RF peaks appeared. Even though our beam was properly aligned with the detector, the ESA we used was older and unstable and couldn't capture both peaks in a single sweep, so we had to record the top and the bottom peaks in separate runs. Using the ESA, the difference between the peaks was equal to L, and we calculated our cavity length shown on the right. The physically measured laser cavity on the left gave a drastic difference that had to have come from our ESA, since we were unable to get two peaks to show in a single reading. Still, this experiment showed us how the ESA can measure laser mode spacing through electrical beat signals.